Thank you. All right. So, not like they all right. So for some of there might be a few new people here who weren't at our earlier seminar, so just the 5-second summary of what we're doing. We're having a workshop here with faculty from all across the country who are interested in bringing cutting-edge science into their teaching of undergraduate students. And so we have several speakers, and Amy Prieto will be speaking for us next, and we're going to, she in particular has chosen a paper for us that she'll present, and then we'll have a discussion. So it'll be 45 minutes of talk and 45 minutes of discussion. So for our guests, you're welcome to stay through the whole thing, or if you want to just stay for the talk and leave after the 45-minute talk and not stay for the discussion, that's okay as well. So this is a real pleasure for me to introduce Amy. So let's just see how we're doing here. There's her name. So she's from Colorado State University and flew here at some stupid hour of the morning to get here yesterday and made it. We were very happy. In her career at Colorado State, and even before then, she's won a lot of different awards. So when she was a postdoc at Harvard, she was one of the first L'Oreal USA for Women in Science Fellows, which I thought was a very cool thing. She won a career award and founded her own company. So sometimes people wonder, it's like, how do you do all these different things? And I'm really not sure, but I'm very impressed. And then on top of that, other types of fellowships that she's been awarded, and then the biggie here, excellence in storage technology. I mean, that one was, I bet you told your mom about that one, you know. And then one recent one that I was very proud of was a mentoring award that she got at Colorado State. So congratulations on that. So that's a little bit of her background. It turns out, I don't know how much of you know, so Amy was actually born in Bogota, Colombia. And so those were her formative years were spent there. And then she moved from there to Grand Rapids, Michigan, which is close to where I live. And talk about culture shock as a child. And then went from there to Williams College, which is one of the top liberal arts colleges in the country. And then from Williams College to UC Berkeley for graduate work. But before all of that, I just want you to know, while Amy was an undergraduate at Williams College, I had the privilege of working with her in undergraduate research. And so this was, she came back to Michigan and was one of our REU students at Hope College one summer. And so just so you know, you got to be careful, right? So here were the two students I had this summer. So Amy, who's gone on to be a very successful professor at Colorado State University, and then Kate Verhey, who is now my children's pediatrician. And so, yeah, she's the best. She has 2 little kids. They're adorable. So it was a really fun summer. This was just a couple years ago. And just to show just how much fun the summer was, too, there's after events as well. And notice that's me sitting on the edge because I think I was about 6 months pregnant with my first one, and I didn't want to get in the hot tub with him. So I think I'm wearing one of Will's shirts there or something. And so it was a great summer, and I'm very, very proud of all that Amy has gone on to do. So if you could please join me in welcoming her. Let's see if Carl takes me.
Okay. So I want to first thank you all for coming, but especially the IONiC leadership group for inviting me here. I taught inorganic chemistry for the first time this last semester, and I used Viper a ton. So I want to thank you and the community basically for providing me a cheat sheet for how to teach this class. I'm actually going to start by giving you a little bit of my background, but what I wanted to highlight before we get going is that when I get to the research part, everything that was done that I'm going to show you was done by this incredibly talented graduate student, Shannon Reha, who very unfortunately graduated finally. It's sad when I still haven't recovered. She's now a postdoc at Argonne National Labs. So I do want to highlight her before we get going. I'm going to try very hard to be done in 45 minutes, but please interrupt me with questions as I go, particularly if I use a word that you're sure what I mean. Please ask as we move along. Okay, so to give you my background, Joanna already, I didn't even remember those pictures from the RU program. What I remember from this summer was that it was my first experience with inorganic chemistry. I hadn't even had inorganic yet. So at Williams, inorganic is typically taught the spring of your junior year. And that is one of, I think, the challenges, I would say, for many of us who teach undergrads is students get to see organic chemistry early. They get to see PChem kind of at a reasonable time. Organic comes so late that it's, for many students, if they're excited by it, they still may not choose to go to graduate school for inorganic chemistry because it still seems too new. And so I want to talk about that. So what I remember from that summer was the first time I pulled glassware out of the freezer and had grown incredible deep red crystals. And that's when I decided this is what I have to do. Now, it turns out the crystals I grow now are all black and they're really small, so you can't see that. They're not nearly as spectacular, but that set me on inorganic chemistry. As I progressed on, I realized I didn't care as much about the organic shrubbery on the outside, so I moved toward solid-state chemistry to try to get away, kind of as far away from carbon as I could, and you'll see that as we go. So what I teach at CSU is general chemistry. The big class, 111, I teach in the spring. And so the challenge is that many of those students either didn't have the math to take Gen Chem in the fall, or they've already failed once. So my best teaching evaluation told me that, said something like, Professor Prieto is so clear, I finally understand everything, and this is my third time taking the class. So you could argue it actually had nothing to do with me, but my goal in that class is to teach well, but really it's to get students to come and be excited, because many of them are not chemistry majors. I do get the privilege of teaching the majors section. We have majors only sections for Gen Chem and Organic that are capped at 40, and so that's where I try to recreate kind of a small college feel. I teach a class called Introduction to Nanotechnology, which is a course that I developed. It's meant as a junior-senior level elective, and it draws from science majors from chemistry, physics, and engineering. And some of what I'm going to show you today, I teach in that class as an introduction to sort of understanding solids and then working back to nanoscale materials. This is the class I got to teach this spring for the first time. This is the book that I use, which is historically used in our department. And I'm showing you that just because I know many of you know this book, the prerequisites are just general chemistry, so we assume that they don't know anything about organic or physical. And fortunately, it being at such a large university, the curricula for Gen Chem is pretty set in stone. So I know exactly what they've had, or at least what they should have had, and I can teach from that. So some of what I'm going to show you is what I used this semester in inorganic. Now, in the past, that class was mainly taught as coordination chemistry and main group chemistry. There was no solid state in it, although there's a big chunk in the book that is solid state chemistry. So I was the first to really try to teach solid state at that level. Most of my class were sophomores, and so my goal was just to get them excited. It wasn't necessarily to teach them everything about bonding, because they have a second semester of inorganic chemistry at the 400 level that they take later. My goal really was just to get them to come and have fun. And then I also do teach a solid state, graduate level solid state chemistry class. So for today, what I'm going to start with is just how I introduce solid state chemistry at the undergraduate level in a very truncated form. So this is meant just to show you kind of my thinking for how to introduce students to the idea and hopefully spur questions. And I have lots of slides I'm happy to share with anybody that continue on from the themes that I'll show you. Then I'm going to try to get you excited about solar energy and how solid state chemistry can contribute to the field. I will highlight the synthesis methods that are used in my field, and Ray did a beautiful job of that, so I'm going to maybe shorten a little bit of that, and also the characterization methods. And I think you'll see, in terms of philosophy, Ray and I are very much alike, and so there will be a lot of the same commentary about the field. Okay, so I always start with something like this. I'm trying to get students to realize that not everything is a molecule, and so I can explain to them that they all agree, say, methane has a carbon with 4 hydrogens around it. They should remember VSEPR theory and Lewis dot structures. We agree that CH4, for example, is very different than, say, CH3OH, and properties are different. We talk about things like water versus hydrogen peroxide, so they agree that the stoichiometry is important and the shape is important. So then I show them structures like this, and the point of it is to highlight that in solid state chemistry, we cannot do what organic chemists can do really in terms of predictive synthesis. So we rely a lot on periodic chains. So here I'm showing you a family of aluminum halides. So the top left, aluminum fluoride, then going to the chloride, bromide, and iodine. I remind them of periodic trends so they can tell me that the halides get larger as you go down the periodic table. And we talk about the fact that this is a 3D structure, so it's interconnected in X, Y, and Z, whereas aluminum chloride are 2D sheets. Then by the time you get to the bromide and the iodide, these are actual molecules. So I asked them to predict for me the melting points of these solids. And I use clickers a lot in my class, so we vote, we argue about things. And then I show them what the melting points are. And this is the first time usually that I can see people kind of light up because it's surprising. When you go from aluminum fluoride, melting point of 1290 degrees Celsius, that's high. And so getting them to think about the fact that things actually do melt at those temperatures is another goal of mine. So try to convey that a lot of the same techniques are used in all chemistries, but for us, we can't just use, say, a melting point system like the way you would for organic in this case. Then going from fluoride to chloride, the melting point drops dramatically, and that is because now between layers there are these really weak intermolecular forces. So I remind them that they should remember all the intermolecular forces and relative strengths. And then by the time you get to the aluminum bromide, which is a molecule, melting point's pretty low, but then the melting point goes up a little bit. And I love picking trends like this where there's a change or a kink, and we talk about why. And in this case, I remind them that iodide's a lot more polarizable than bromide is, remind them of London dispersion forces, and so there are a lot of basic Gen Chem ideas you can take, and all I do is I take the CRC and I pick something like a melting point or boiling point, and I try to pick families that I think have interesting trends like this. They've all seen this actually at the very end of Gen Chem. They've seen a basic molecular orbital diagram of hydrogen. So we talk about how you're taking two orbitals together and combining them in a linear combination. And we talk about how you fill in the electrons then once you come up with your molecular orbital diagram. My big thing is energy as an axis, and we talk a lot about energy. So they know this picture. So to introduce solid-state chemistry, I use Roald Hoffman's book, and I know Maggie showed you that yesterday. This is just, I think, the most intuitive way to explain band structures to chemists. We are all pretty comfortable thinking about orbitals, and so I show them, remember, this is just the MO of hydrogen. So now we do a thought experiment where we just add a 1s orbital, so now we have 3. You have to conserve the number of atomic orbitals you start with, has to equal the number of molecular orbitals you end with. We build them up. We agree, at least at the level I teach this, that we're not going to talk about group theory. So we don't talk, they have not had that yet. They'll have it at the 400 level course they take. But they do get the idea that you get combinations, and if you get a really big chain here, and you wrap it into a circle so that there are no end atoms, they do know nodes. They understand nodes from Gen Chem. So we talk about how the lowest energy combination is the all bonding combination, and the highest energy combination is one where there's a node between every orbital. So they get that, and they agree that it makes sense that if you had Avogadro's number of these, there would be a lot of orbitals, and at some point we're just going to draw that as a band. I like to use literature papers in my class a lot, and so I do want to explain to them what K-space is, only because by the end of the semester I can usually give them a physics theory paper with a calculated band structure that looks super complicated, and they can at least pick out band gaps and tell me generally what the properties should be. And so in order to do that, you kind of do have to explain K. I explain it just as a way of keeping track of your combinations. We talk about how if we made this chain now and put a 1s orbital at every lattice point, again, the all bonding combination, the all anti-bonding combination, so they get that. Some of the students who are more mathematically inclined like these equations and they like reading more about them. Some have a challenge with the math, and we talk about how that's not so important. What I want them to be able to do is draw the pictures. So then we go to plotting K versus energy. And again, all bonding combination, they intuitively tell me makes sense that it should be the most stable, so lower in energy. The anti-bonding combination then should be higher in energy. And so I tell them, all you need to get from band structures are these two key features. The width, so the change in energy has to do with how well the orbitals overlap. And then the way the band runs, in terms of it going up or down in energy, has to do with topology. So I give them a problem set question where I ask them to do the same thing, but with a p orbital in one dimension. And when they do that, they figure out that that runs the opposite way. So if I take this p orbital and I add it, now there is actually a node between every orbital. So that one must be high in energy. And when I go to the plus minus combination, now you actually do get bonding interactions on either side of the p orbitals, and that one's lower in energy. And so what I build off of this is we do the exact same thing in Roald Hoffman's book, potassium platinum chloride, which is a 1D compound that interacts through the dz squared orbital. They can predict which one should overlap really well and get a big spread, which one shouldn't overlap very well at all and get a small spread, and from that you can basically sketch out the band structure. And the point is to show them you don't need a complicated computer program, you don't need to understand quantum mechanics, because chemists are good at drawing pictures, and they should all know what the orbitals are. They do know what the orbitals are. So, we talk a little bit about, again, degree of overlap. And so we talk about how if you put these hydrogen 1s orbitals really far apart, there's not very much overlap. So that means that the bonding combination is not great, but the anti-bonding combination is not that bad. As you start pushing them closer together, the bonding combination is good, the anti-bonding combination is bad. And if you get them too close together, you start getting some repulsion. So the good combination is good, but it's not great, and the bad combination is very high. And actually, I like to show sort of exotic experimental setups just because they're kind of exciting. So this is where I talk about high pressure research and diamond ampule cells and how it's an amazing way for chemists to get to control bond length, basically, with just one compound. You can squeeze things to make the atoms really close to each other and look at what the physical properties are. So this is my whirlwind tour of band structures. Then I remind them, okay, if we don't want to worry about K, we can basically just say all we care about is the spread in energy, and that's how you get these sort of rectangle pictures like what Maggie showed you yesterday, and you can talk about band gaps and what are metals and semiconductors and insulators. Okay, so I do compare real space and reciprocal space because reciprocal space tends to be how physicists think about things. Real space tends to be how chemists think about things. And I want them to know the language because I think it's important to be able to understand the language of scientists in other fields. And basically, I'm not going to read through all of this, but each of these points in terms of what information you get from what kind of a model is usually related to a couple of clicker questions or problem set questions. And nanotechnology is actually a really cool tool to teach this because nanoparticles kind of fall between molecules and solids, and I like to try to highlight where models maybe break down or have inadequacies. Okay, so now let me start then on the research part of things and what my group does. So I think it's probably not difficult to convince any of you that we use a lot of energy, and that's actually problematic for many reasons, one of which is where we get our energy, and the other is how we store it. I do like to show units. So you can imagine, say, your laptop's on the order of 1 watt in terms of the power that it uses. Anything that uses resistive heating is pretty inefficient, like your toaster. So that's about 1 kilowatt, and you can go all the way to the planet, and we use on the order of 15 terawatts of power. And that's a really big number. 80 to 90% of that comes from fossil fuels, and so here I'm plotting parts per million in terms of atmospheric concentration of CO2 as a function of year, and you can see we're up pretty high, and the shape of this line, I don't usually like to, I try to avoid talking about politics in my class, but I like to show plots like this because they're hard to argue with. So the point here is that it's predicted that we're going to need about 30 terawatts of power by 2050, and that's just not going to be sustainable if we take it from fossil fuels, not only in terms of how many, or the amount of fossil fuels we have available to us, but in terms of what we're doing to the atmosphere. It's pretty clear that we're going to need to think about a different way to do things. So many people are turning to renewable energy, and I use renewable energy a lot in my classes because Colorado is a state that tends to be fairly progressive in terms of renewable energy. So what I'm going to focus on for today is solar power. That's the topic of the paper that I suggested for the workshop, and I wanted to pick an example that I see a lot. This is the Denver International Airport, and these are these solar fields that they've recently put in. So the way it works, you drive into the airport here, and this is the exit. DIA is on the plains. We live literally where the Great Plains hit the Rockies, and what's important about this location is we get about 330 days of bright sunlight a year. So it looks like this almost all the time. These solar panels are very large. They span 11 by 4 football fields. It's about 9,200 panels. They do track the sun automatically, so they're on these hinges. So they start angled toward the sunrise, and then they do track the sun during the day, and they follow it to sunset. They are about 9% efficient, and that's because they are polycrystalline silicon solar cells, which are the common solar cells available commercially. They provide 3 million kilowatt hours of energy, and they reduce the carbon emissions of the airport by about 6.3 million pounds per year. So these numbers seem really impressive. Again, you have to think, though, about the units and relative to what. So if you look at that, it's only 2% of the airport's annual energy needs. It's about 4% at peak time. And that's pretty depressing. So you could ask the question, why is that? There's so much empty space out there. Why didn't they just put more solar panels in? The reason for that has to do with the cost. So this is solar in terms of cents per kilowatt hour versus wind. We get a lot of wind energy from Wyoming and Montana, and natural gas. And very unfortunately, our state seems to be leading the charge in terms of fracking. So we get a lot of energy from natural gas. And so the point here is that the upfront cost of solar energy is prohibitive enough that most people don't want to install solar panels, even though you can argue this will pay off over X number of years. And so this is actually a problem set I give students sometimes in terms of unit conversions. How long would it take you to pay off the solar panel depending on how much power you generate? Now this, again, is not something I would show typically in a research talk, but I do show it in my class because in solar papers a lot people talk about 1 electron volt being the optimal band gap or 1.5 eV being the optimal band gap. And so I always want to talk about why that is. So if you look here at spectral irradiance versus wavelength, the gray line is what you would calculate from the black body spectrum of the sun at 5200 C relatively. The yellow here is the sunlight that hits the top of the atmosphere. And then when you attenuate that with the molecules in our atmosphere that can absorb at the various wavelengths, so water, oxygen, CO2, what you get is the red. And this is the spectrum that hits the Earth. So a 1 eV band gap, you have absorption at about 1200 nanometers, 1.5 eV, that's about 827 nanometers. So we talk about sort of the visible wavelength, visible spectrum, and they know that from GenCom. Now, if you look more specifically at the spectral irradiance again, but convert the x-axis to photon energy in terms of electron volts, what's important here is this 1 to 2 range is the best for absorbing the most intense light coming from the sun. And here I'm showing you the visible spectrum as well. So my point to the students is don't just memorize numbers. Try to think about where the numbers come from and the practical implication of that. So the point here is that if you have a solar cell where the absorber material has a band gap that's too small, you don't absorb kind of the most photon flux. If the band gap is too large, again, you don't absorb the best range in terms of photon flux. So we want something that's tuned to be in the right range. And that leads into discussions of the design of synthesis and targeting what you want to make and why. There are many types of solar cells, and this list I'm showing you only because I have projects in my class, typically in the nanotechnology class, where students have to write a paper and give a presentation on a topic of their choosing, and usually we gear that around recent literature. And so here what I'm trying to convey is just that there's no one way to make a good solar cell. There are many, many approaches and huge research communities in each field. So here I'm showing you the cost in US dollars per meter squared of the solar panel versus the efficiency, and these are calculated bubbles. So bubble 1 are first generation materials. These are silicon, they're usually flat plate. These are the most common, and they range anywhere from $3.50 per peak watt down to about $1.25. Generation 2 materials are thin film solar cells, like what I'm going to show you today, usually composed of materials that are better or more efficient at absorbing light than silicon is, and the goal there is to be able to use a lot less material. And then we have third generation materials, or third generation cells made of really novel materials, dyes, conductive plastics, using things like solar concentrators. And so this is just a way of showing you how large the field is and kind of where I would say researchers in this area are moving. There's a really great, it's not really a review paper, but it's a paper you can Google the title here, The Silicon Solar Cell Turns 50, and it describes kind of all the research that's happened from the first solar cell being developed at Bell Labs to now. Okay, so in terms of these second generation thin film technologies, the motivation in this field is that silicon cells require a lot of material on the order of 100 microns of silicon, and that's because silicon has an indirect band gap. So it's not very efficient at absorbing light, so you need a lot of it. Silicon is incredibly naturally abundant, but we get it from sand, which is SiO2, and sometimes I show the commercial pathway to go from raw quartz all the way to silicon, and there are lots of steps at very high temperature using very caustic chemicals. So that's why silicon, even though it's really abundant, is expensive. So people are looking at these second generation materials because they have direct band gaps, so you don't need as much material. And the hope here is that if you don't have to use as much material, you can make a cheaper cell. So here what you see is a cross-sectional scanning electron microscopy image, which is false colored to show you the different layers. And the key here is that we need a layer that's going to absorb material that's p-type, a layer that's going to absorb sunlight that's p-type, and a layer that's going to absorb sunlight that's n-type, and we need current collectors on both sides to actually collect that current. But the current collectors, at least on one side, have to be transparent if you're going to get the sunlight in. So here you see a conductive transparent oxide down here, cadmium telluride, which is the main absorber layer in this case, p-type material, a thin layer of cadmium sulfide, and then we have our tin oxide, which is the current collector at the top. In this case, copper, indium, gallium sulfide, or selenide. Again, you only need 1 to 2.5 microns of it because it absorbs light really efficiently. In this case, molybdenum is the current collector on the bottom, and then indium doped tin oxide, which is a conductive transparent oxide on the top. So the Department of Energy has set a cost goal of about 33 cents per peak watt, and I showed you on the previous slide that the best solar cells right now are at about $1.25, so we are nowhere near the cost goal. And so the goal really is not only using better materials, using less of them, but figuring out ways to make these solar cells that's cheaper. And so what I hope I show you today is, although people are really thinking about it, some of the techniques, including my research, really are not cheap if you think about the chemicals that we use. So I think the goal of the paper that I picked was to try to, or at least our goal was to try to understand the physical properties of a material and how we could control them in synthesis, but it was not intended to make a commercial product, and I will highlight why that is. Okay, so when we were starting in this field, in the research group, I wanted to pick a problem that a solid-state chemist could contribute to. And so what we did is we made a list of the compounds that were of interest, and we started doing research on review papers and what people thought of all these different solar absorbing materials. And I would draw your attention particularly to this paper by Wadia and Alvisados. It's in Environmental Science and Technology. It has a very interesting mix of science and I would say business in it, in terms of calculating costs of things, and that can be interesting for students. You know, in our Gen Chem classes, about 80% of our campus has to take chemistry for whatever reason because of their majors, including people like fashion design majors and some of the business majors. And so mixing in papers like this is often a good way to draw their attention. Now, in this paper, what they did is list a bunch of second generation materials that all have direct band gaps. And so here I'm showing you the compounds on the y-axis. Then they did this calculation on annual electricity. Now that is the potential that each of those compounds has to produce energy. And what's important to know is what they use to calculate that number is the natural abundance of the elements present in the Earth's crust, coupled with how expensive is it to refine it from however it naturally occurs. And that is then coupled by the theoretical efficiency of a solar cell. So these are not measured values, they're theoretical predictions. So that's how in this axis you get a log scale of terawatt hours. So you can see all of these compounds have the potential to produce enough energy for the world's need. Here I'm showing you the U.S. consumption of power and the worldwide consumption of power, and that is meant to have a political connotation to it. We have very, very few international students in our university, or primarily domestic students, and so I just want to highlight for them, I guess, not equitable use of energy and work. So if you look at abundance now of all the elements that go into these compounds, now here, this axis for the top half of the figure is parts per million by weight in the Earth's crust, and you can see all of these are fairly abundant. Then down below is dollars per kilogram. So how much would it cost you to buy a kilogram of that material? And a couple of things stand out. One, indium, for example, is pretty expensive. Two, tellurium is actually not as abundant as you would think. And the third point, and I don't know how I feel about this. This is another, I think, philosophical point. Some people have problems with cadmium because of its toxicity. So places like Germany, for example, you are not allowed to install cadmium telluride solar cells because of the toxicity. In the US, we are allowed to, and there's certainly an argument that these are very well packaged and not likely to end up in a landfill. So I'm not sure how I feel about that argument. But the point here is that the two examples that are in commercial production right now are cadmium telluride, copper, indium, gallium, sulfide. And so what my students and I were trying to figure out is there another compound on that list that we could work on where we could try to contribute in terms of developing a new synthetic approach to the compound that would allow us to control physical properties. And the one we quickly were drawn to is the CZTS, copper, zinc, tin sulfide. It is structurally analogous to CIGS, but it doesn't have any indium or gallium. Copper, zinc, tin, and sulfur are all incredibly naturally abundant, and there's a reasonable argument to be made that they're all non-toxic as well. A compound I am not going to tell you at all about today, but hopefully jumps out, is this one, iron disulfide. You would think this would be the home run. It is incredibly naturally abundant. It has a theoretical efficiency of 20%. We dump it by the metric ton every year from active mines. So in theory, if you could make a solar cell that was only 10% efficient, using pyrite, which is fool's gold, we could power the whole planet. But nobody's ever made a cell that's better than about 3% efficient, and there are some really interesting solid-state challenges to that. But I'm going to talk about CZTS. So this is the structure on the right. I know a lot of you now have a primer on crystal maker. What's important about this structure is it's actually, in theory, pretty simple. I'm showing you copper and blue, zinc and gray, tin and red, and sulfur and yellow. And what's important here is really the ordering. So in this cartoon, which looks very idealized, you have 8 sites that are important. 2 coppers here and 2 zincs here, and then the crystallographically related sites down here, 2 coppers and 2 zincs. So I'm showing you one ordering. By the end of the talk, I hope I convince you that there is nothing in real life that's this simple. And so there's a lot we have still left to understand. But what's important about this compound right now is that it's a p-type semiconductor. It has a 1.5 eV band gap, so again in the optimal range. It has a huge absorption coefficient. So in theory, you would only need 250 nanometers of this material to efficiently absorb the solar spectrum. Power conversion efficiencies. So this is basically if you shine light and you know how many photons are hitting your material and you collect the current, you can calculate your efficiency. One of the first reports had a pretty high one, 6.7%. Within only a year, it got up to 9.6%, and now it's actually above 11%. And so I was interested because without even knowing very much about the compound, it's already performing pretty well. Now, the challenge here is that this 9.6% cell was processed out of liquid solution. And people were excited about that because the thought was instead of kind of the traditional solid-state methods of very high temperatures or using something like chemical vapor deposition to deposit a film, which would be really expensive, could we come up with a way to make precursors out of solution that you could then either use an inkjet printer to put on a substrate or a slot die coater or simple methods like basically inkjet spraying, where you spray a liquid and it dries on a surface. So people were trying to figure out how to do this out of solution. And Dave Mitzi's group at IBM figured that out, except that their solvent is hydrazine, which is jet fuel. And there's no way we're going to build large-scale plant. Well, I suppose people have made plants on those things, but that's not so likely. So the question was, could we develop a solution phase method to make particles of this compound? And then really importantly, what I wanted to try to figure out is, could we tune the copper to zinc stoichiometry? That was predicted by theory to improve the absorption coefficient. So the theory was that if you could make copper deficient zinc-rich compounds, they would absorb light more efficiently. And then the second part was, could we tune the sulfur and selenium? And I'll come back to that. So the paper I suggested for the workshop involved this, but I do want to explain this as a first step because it's important in terms of the characterization methods that we use. Okay, so we make these by the injection methods, just as Ray showed you. And the key here is that at the end, you end up with this nanoparticle where the core is the inorganic piece, the solid state piece, and ideally that's where you can control the electronic properties of your material. The surface is coated with these organic molecules. Again, to highlight that I'm not an organic chemist, this is a cartoon of a very common surfactant called trioctophosphine oxide, where you have a phosphorus double bonded oxygen that's very typical in terms of a polar head group, and then you have these long alkyl chains that are very hydrophobic. And so the idea is that you can suspend these in nonpolar solvents, and then to work up these reactions, what we do is we basically take our mix here, put it into something like hexanes or toluene, and then we crash our particles out with something like methanol, and then we resuspend them, and in that way we rinse away kind of the excess surfactant. So we do have sort of a workup process that's very similar to, I think, molecular systems. But the idea is that we need to figure out what precursors to use, what temperature to use, and what mix of surfactants to use to make the compound that we want. Now, this is an aside. If you want to teach about nucleation and growth, this Alvisato's paper is a really nice review of the synthesis method, and it does have a whole discussion of basically Oswald ripening, so how these particles can nucleate, how you can redissolve them. It has discussions of things like surface energy and why small particles dissolve faster, say, than big particles. And so I use this paper as a whole discussion on the basic thermodynamics, I guess, of nanoparticles. And so this is a good example. But the idea is basically, if you think about size of your particle in a generic way and the growth rate, when you inject your precursors and they decompose and nucleate, if you have a very small particle, it can grow really fast, and then it depletes the amount of, we call it monomer, because we don't really know what's in solution. And then the growth rate is going to tail off. If the critical size, so what you need to nucleate to be stable, so it won't dissolve quickly, is larger, the growth rate's going to be smaller, and you get this. This is the case for low monomer concentration. So the point is that you can control the equilibrium of these particles growing versus dissolving by the concentration of the precursors in solution and the size of the particles. So you can sort of toggle back and forth by adding a ton more monomer to make your particles fall on this red line, or doing your reaction at low monomer concentrations where you'll be on this blue line. So this paper in and of itself, I usually spend, say for my nanotechnology class, almost a week on. And this can tie to like the basic petrol method. Now in our case, I'll tell you how we thought about the synthesis. I think we were very lucky that it worked the way that it actually did, and then I'll add a commentary to something that Ray said about things changing and you can't necessarily control it. So the way we thought about it actually is as an electrochemist. So a lot of what we do in my group is electrochemistry, so I tend to think about oxidation state. So if you look at the compound here, copper 1+, zinc 2, tin 4, and sulfur 2-. So what we decided to do was to try to initiate the precipitation of this compound using a change in oxidation state. We started with metal acetates mixed with oleolamine, which is a very long chain primary amine that has a double bond roughly in the middle. That's might actually be important for the reaction. And what's important here is we start with copper 2. Oleolamine is known to be a reducing agent at elevated temperatures, so we are trying to go from copper 2 to copper 1 to start the reaction. In a separate vial, we mix elemental sulfur with oleolamine, and again, the idea is the oleolamine is going to reduce the sulfur to 2-. And then both of those solutions are co-injected into trioctophosphine oxide at 300 degrees. At the end, we get these nanoparticles. We can measure lattice spacings to try to characterize the particles. You can see that in this reaction, we do not have a good control over the shape. The size is about 13 nanometers plus or minus 2 nanometers. There's actually no well-defined agreement in the field for what a narrow size dispersion is, but this is, in my opinion, something that's important to report. We can take an electron diffraction pattern, just as Ray mentioned, and index all the Miller indices. And if you look at an actual image of Shannon's hand holding one of these vials, the reason these are called nanoparticle inks is because they look like ink. Jet black, that's letting you know it absorbs light. And so it is sort of ironic going from my first love of inorganic, which is all the colors. In my lab, things like green and blue are bad. Black is really good. And so that's how we characterize things. Now, what's really important is to go from this to a thin film. If you're going to make it perform well in a device, you still have to heat treat it at the end. And that is, I would say, the major challenge in this field and something that nobody has really solved yet. Now, X-ray diffraction. We take X-ray diffraction patterns like organic chemists take NMRs. That is the first thing we do. And in this field, or for this particular compound, it is, although not exactly useless, it's pretty close. So the powder pattern at the top shows the peak broad mean, which we use to calculate particle size. You can see it's all indexed to CZTS. We generate the reference pattern from a single crystal structure. But look at what's important. The common impurities that you could have are copper tin sulfide and zinc sulfide, and they have basically identical diffraction patterns, at least identical to within what our instrument. We have an ancient powder pattern, or powder diffractometer. So I think, I don't know how you would necessarily turn this into a learning object, but I think it is important for students to think about what data is used in papers and whether or not it's sufficient. There are a lot of papers, including papers in JAX, on CZTS that only show a powder pattern as their characterization method. And I would argue that that's not sufficient because these two compounds have small band gaps. So if you put a device together with a mixture of these, it will never perform well. And if you don't know that those impurities are present, you won't be able to troubleshoot why your films aren't very efficient. So we use a variety of characterization methods. We use energy dispersive spectroscopy in our SEM to get an idea over large length scales if the composition is uniform. X-ray diffraction can be used to eliminate tin sulfide as one of the impurities, so again, it's not totally useless. We use X-ray photoelectron spectroscopy not only to quantify what elements are present, but also because copper 1+ and copper 2+ give very different XPS spectra, and this lets us know if our particles are oxidizing in air or not. But what's really, I think, in some ways, the stupidly simple way to figure out if your particles are pure is basically to take a melting point. Now, we used a differential thermal analysis instrument, but I told you at the beginning, very high melting points, for solids on the order of 1,000 degrees, you can't really take a reasonable melting point in a normal instrument. But nanoparticles exhibit reduced melting points, and that has to do with the surface energy on the surface. And so that in and of itself is a whole class activity that I do, where I show a range of gold at different sizes and the corresponding melting points, and we talk about why that is. So in this case, the particles are small enough they melt at a reasonable temperature. And so just like an organic chemist would take a melting point, we take a melting point if there's only one clear, well-defined melting point. It's a good indication that our particles are pure. If we see multiple melting points, we know that there are impurities present, and so then we can go back to the synthesis. Now, I make it sound like this is incredibly controlled, but I would like to go back and highlight this surfactant, which is just the most annoying surfactant I think present. So this reaction worked beautifully for like a year and a half. And then the company we were buying olealamine from ran out. So we bought a bottle from another company, and the reaction just didn't work at all. We got to that eventually, yeah. So it turned out we had a big bottle, and Shannon was pumping in a small jar to the glove box every month or so, and that worked fine. So the new company, it didn't work. And that bottle, it said was 70% pure. And the bottle we've been using before was 90% purity. So I thought, okay, well, we'll just purify it. So olealamine is an 18-carbon chain. So we distilled it. And the problem was we got it almost too pure. And so then the reaction didn't work either. Then the old company, and I'm just telling you the story because this is not the first time in this field that this has happened. Certainly, and not even, I mean, other surfactants have shown this as well. It's, oh my goodness. So I thought, okay, well, this will be, we'll just pretend we're organic chemists and we'll take NMRs and mass specs and we'll figure out everything that's present. So that was a problem because then we figured out we had every primary amine going from 18 carbons down to 6. And so, and then we found out, okay, well, these are primary amines, and when you expose them, say, to CO2, you can make carbamates, and we were trying to figure out if that was important. So the old company started making oleylamine again, same nominal purity, and the reaction just didn't work again. And what I mean by didn't work is we're making mixtures of things. So we now think some of the acids that are present would be important, and it turns out aging seems important. So when it's brand new, it doesn't work. If you let it sit for a week, then it works. But if you let it sit too long, it stops working. And so I go to my organic colleagues and I say, how do we figure this out? And as soon as they see that 300 degrees, they say, I have no idea what you're doing. And so my point is just that it is an interesting challenge, actually, because I told you melting point is the best way, but we never took melting points of every reaction. We took melting points kind of after batches. Now that we know better and we do this every reaction, we are seeing sometimes very small traces of other phases present. And so now we're trying to figure out, in a way, do we know too much? I mean, is it now we're just paying too much attention, and before maybe all this was happening we didn't know? But it is an interesting discussion to have in the class in terms of older fields, like, say, synthetic organic chemistry, tend to have well-defined ways of, like, when you publish a paper, this is the characterization you need to show, and this is how. Nanoparticles research doesn't have that, and so it varies pretty wildly, and I think it's sort of a discussion our community is having now, is what's important and how should we report it. So what we are trying to write now is sort of a review paper, but using our data and data from other papers, showing kind of a logic tree. For this particular compound, start with X-ray. That can eliminate tin sulfide, but you're still left with these potential differences. And then going through kind of all the different characterization methods and figuring out how to eliminate it so that we get down to an understanding. So, okay, so that's my commentary on oleylamine and the surfactants that we use. And Ray, I was just like nodding loudly as you were talking. We know the reactions generally work, but we can't tell you what's happening in solution, and we don't really have a sense of reaction mechanisms, although some people have published beautiful papers on, okay, at the very early stages of the reactions you can isolate these solids, and later stages they convert to these other things. So we're kind of working on it. So now let's jump back to the research. So I just showed you we made copper zinc tin sulfide particles. Now we want to characterize the properties. And in my group, we tend to make things and then we put them in devices, because a lot of the spectroscopy and X-ray diffraction, as Ray mentioned, can tell you a little, I mean, it can tell you a lot about your material, but if what you want to make is something like a solar cell, what you care about is how well can you collect current. And that involves interfaces and where they can be combined. And so it helps us improve our synthesis if we can make kind of a rudimentary device, figure out how well it works, and then we go back to the synthesis. So in this case, we want to make a thin film. So we have these nanoparticles with the organic surfactant, but they are really insulating, these long-chain organic molecules. So we need to get them off. So what we do is we take our transparent conducting electrode, that's going to be our current collector, we dip it in our nanoparticle ink so we get a thin layer. I don't mean to imply it's a monolayer. It really is single layer nanoparticles. I just mean to say it's thin. Then we dip it in another solution of a high concentration of some short chain linker. So something like ethylene diamine. The idea here is that you have a polar head group on both sides so that hopefully some of the time it sticks to two particles and it stitches them together. These kinds of ligand exchange reactions, this is all equilibrium. I mean, this is something that freshmen and sophomore can think about. So you stitch the particles together, then you dip again, and you make another layer, and then you dip again. And in this way, you build up this, it's called layer by layer dip coating. It's one method to make particles. We used to have undergrads that did this. But the films we want to study as a function of thickness, that can correlate to how many times you dip. and the films that turn out to be the best have to be dipped somewhere between 100 and 200 times, and that is not a good use of trying to teach an undergraduate research. So we actually have a little robot that does it. So Shannon's father is a machinist, and so she told him, and that's the most effective. If you can have one of your graduate students or undergrads have a parent who's in charge of the instrument, the turnaround time is amazingly fast. So Shannon's dad built this really cool little robot that can dip up to four different vials, and you get to set a rate and you get to set a time, and then you just start it and you can walk away and do something else and come back. So in that way we can build up films as a function of thickness. This is what they look like. So the top is you're looking at a plan view of one of these films. Note that it's pretty rough, which is good. It looks kind of like black velvet, so it doesn't reflect light well. It absorbs it, which is great. The cross section in this particular case, this is glass, fluorine doped tin oxide, which is our current collector, and then about 125 nanometer thick film. So we can study a lot of electrochemistry as a function of thickness. We take an absorption spectra, and so what you see here is absorbance as a function of wavelength. You see nice absorption over a range of wavelength. You see kind of a well-defined absorption event here, and the hints of a smaller one at high energy. The way people figure out band gaps in this field is to take the absorption coefficient times h nu squared as a function of energy, and then you look for the linear region and you extrapolate that down, and that tells you your band. Now what we have figured out now that we're learning more about this kind of spectroscopy is if you have mixtures, they don't necessarily show up by this analysis because the absorptions can overlap, and so you can't really decouple them. But when it's nice and clean, it's sort of reasonable. The band gap we get here is about 1.5 eV, which is consistent with what what's predicted for the bulk. The band gap of one of the impurity phases I showed you before, just as comparison, is about 0.9 eV, so again, a lot smaller. We have intentionally made mixtures of different combinations to get the right overall the right stoichiometry, and the absorption is really messy, and so at least we can do that as a control. Yes, I will get to that. That comes from different batches. Yeah. Another problem with if you learn too much, then you get yourself confused. But I will get to that. So the paper preceding the one I suggested for the workshop is where we wanted to show control of the metal stoichiometry. Now remember, theorists had predicted that if you make this compound copper deficient and zinc rich, the properties should change. The reason I love showing that, again, going back to the molecular analogy, you would all agree that H2O is not the same as H2O2, but in solid state chemistry you can play with pretty big ranges sometimes, and the properties can be different. So in the solid lines, let's just look at that first. Again, wavelength is a function of absorbance. The red here is the UV vis that I just showed you. Excuse me, the black. The red here is the copper deficient sample, and already you can see that it's absorbing more light. The particles were the same size, the same standard deviation, same size distribution, and the films were the same thickness. So the only difference was the composition. Notice that I don't use a lot of significant figures for composition for all the reasons that Ray mentioned. We do use standards with our EDS, but even those have composition ranges, and so people who show 3 and 4 significant figures for EDS haven't thought about limits of sensitivity for that technique. Now, for reasons I'm not really going to explain today, we figured out that our films were slightly porous, so we had to do a mild heat treatment. When we heat our particles, we get the dotted lines. You see an improvement here for the stoichiometric sample, but you see a pretty dramatic improvement for the non-stoichiometric sample. So the point here is that controlling the metal composition does control the electronic properties, and you can link that back to ideas of bonding. Now, we don't build full solar cells, we do photoelectrochemistry because it's much simpler and we only have to deal with one interface. So here's the idea. I know you guys saw valence bands and conduction bands yesterday. So to simplify, this is the top of the valence band, this is the bottom of the conduction band. What we're going to do is use light to excite an electron and create an electron-hole pair. This compound is a p-type semiconductor, so we want to collect the holes. So we're going to sweep our electrode to negative potentials, and so the holes are going to go into the electrode. But now we're left with these electrons, and we need to do something with them. So in solution, we have europium 3 plus salt. We'll start with europium nitrate. The idea here is that I can collect the holes and measure that as current. The electrons are going to reduce europium 3 to europium 2, and then that redox couple is going to be regenerated at my counter electrode. So we use a simple 3-electrode cell. This is the little alligator clip, and the little film is here. We have a reference electrode, so we know what potential we're referencing to. And a counter electrode, we use either green light, because it's the middle of the visible spectrum, or we use a white lamp that mimics the solar spectrum, and we can count how many photons are hitting our sample. So when we do that, the black is the as-deposited film. And before I show this to a class or something like this, I usually teach a little bit about cyclical chemistry and what that is. So this is just half of the CD basically. And what you see is the top of the line is when it's dark. The bottom of the line is when the light is on. And you see there's more current when the light is on, which means you are exciting charge carriers and collecting them. This is the as-deposited film. When we heat it, you see the dark current goes away, and the photocurrent is much higher, and it's much better over time. So this inset is a constant potential, and we're just turning the light on and off. And you see that this compound is actually producing about a 10 times higher photocurrent after you heat it, and it's pretty stable over many cycles. Now, when we then take that data and calculate how many photons are hitting the sample, that's the incident photon part of this, and then the current efficiency. What's important here is that the copper deficient sample that was heated is much more efficient over a much broader wavelength. And we don't actually know why that is anymore. Again, we looked at these particles really carefully to study the composition and the structure, and it turns out to be a much messier picture than the parts we measured before. But what we do know is that we can target a stoichiometry and get better properties. And I think that's kind of the important first step in here. Okay, so let me highlight one more thing, and I just have a few more pictures to show you. The paper that I suggested for the workshop involved our efforts now to tune the chalcogen site. And the reason for that is, again, these power conversion efficiencies. The best devices are made out of this hydrazine-based liquid, and then they're heated in selenium vapor at 540 degrees Celsius. And that just seemed really odd to me for many reasons. The selenium goes on the sulfur site, and it essentially replaces all of the sulfur, although these films are typically not analyzed for composition after this heat treatment step. What is known is that when you heat it at that high of a temperature, you go from nanoparticles to large grains, microscopic grains, and those have much better transport properties. So instead of all these interfaces between nanoparticles where you can get recombination, you have these micron-sized crystals and much better electrical conductivity. However, there's a theory, several theory papers that say that when you put selenium in on the sulfur site, so replace all these yellow spheres with selenium, the band gap should drop to 1 eV. And it seems like that shouldn't be, that's not ideal for nucleics. So what we wanted to do was come up again with a solution synthesis route where we could control the amount of selenium in our particles and then study the physical properties as a function of composition to figure out why the selenium was so important. So, not to harp on Shannon's talent, but this is incredible. Many solid-state chemists, the more elements you get into a compound, kind of the more macho you are. And I've never seen 5 elements in one nanoparticle sort of in a controlled way. And so this was what Shannon, she wanted one more project before she graduated, and I suggested this as if you hit a home run, it'll be fun, and if it doesn't work, it's okay. But she figured out how to make this work. Now, I told you we used allylamine as a reducing agent. It does not reduce selenium, so you can't dissolve it. So she had to use allylamine for the sulfur, sodium borohydride for the selenium. So now she had 3 syringes she was injecting at the same time. And she did a lot of controls to try to make sure this was actually real. So here are the data just for the X-ray diffraction. Keeping in mind it has all the challenges I showed you before, but at least the lattice shifts are important here. In black is the 100% sulfur. The red is 10% selenium, 50% selenium, 90%, and 100%. And you see a shift to lower 2 theta, which means a larger despacing. This follows Vigard's law. which is a law that basically says if you take a unit cell and you put a larger or an atom in of a different size, the lattice parameter should change in a linear fashion. So you can, in theory, use the lattice parameters to calculate composition. And this is kind of a cool exercise to have. I usually have students do it with sodium chloride and potassium chloride, because they have the same structure. But this is the exact same idea. And the fact that it shifts in this linear fashion was an indicator that we were actually getting both elements into the same particle. Again, the powder patterns, for all the reasons I showed you before, I just wanted another method to corroborate this. So Shannon looked at nanoparticles of all the different compositions. So this is the 100% sulfur, then 10% selenium, 50, 90, 100% selenium. She measured the width of the lattice spacings. And this is where we did put error bars on things. So these are, she measured at least 100 particles from 3 different batches that were made on different days and from different bottles, just to try to make sure we were seeing something real. We fixated on the 112 lattice plane because that's the common one to both the structures, and that's the one that varies linearly, and that's how we get these error bars. So the error bars are pretty big, but at least it shows that the trend goes in the direction that we would expect. Now, this is a lot of data, but this is where I highlight kind of lack of control in a way. The first thing we noticed, if we look at the copper to zinc ratio, is that we sort of lost our ability to control that in terms of making all the particles copper deficient and zinc rich. We have tried ICP-MS to do elemental analysis, and our particles don't dissolve well. Various things precipitate out. So more, I would say, elegant elemental analysis we haven't figured out how to do yet. So this is done a combination of EDS and the SPM, SEM, and XPS. So again, big error bars, but the trends show that we don't really have good control over that. But the surprising result was the band gap. So I told you that if theorists predicted 100% selenium should give you a band gap of 1 eV, and you don't see that. You do see a decrease, but not by as much as you would expect. And this part, I still don't really understand. Papers have come out since we published this where they do show a 1 EV band gap for copper, zinc, and selenium. So I'm not sure. I think this might have something to do with the way the band gaps are calculated from the UV vis spectra. So we have a lot more thinking to do in terms of this. But the trend at least matches theory. And we did put error bars on that. So again, in terms of measuring the band gap using UV vis, multiple batches from different days and different bottles, and the trend again decreases, but we never get down anywhere near 1 EV. So the band gap doesn't change a lot, at least for these nanoparticles. So we wanted to know, so selenium must be doing something, and we're trying to figure out what that is. So what we decided to do is measure conductivity of these nanoparticles, not replacing the organic ligands, but just pressing a pellet, so a really crude conductivity measurement. And here what you see is starting 100% sulfur, 10% selenium, 50%, 100%. Basically the conductivity increases by about 3 orders of magnitude. And so we think that the incorporation of the selenium is really important for tuning the conductivity. And that would lead to a much more efficient solar cell. And so this is our current kind of hypothesis. In the paper you'll notice we listed, I think, 3 hypotheses for what the selenium is doing, and we were trying to be systematic about eliminating the ones that we could. We are doing a lot of work now on thin films of these nanoparticles using electron beam lithography to pattern electrodes. So this is a cartoon of what these patterns look like. If you zoom in, there are 2 gold electrodes, and we deposit nanoparticles on the surface. This is copper selenide, so a different compound from my group, but the idea here is you can do really quick current voltage measurements, and what we use those for is to correlate our ligand exchange reactions to enhance conductivity, to figure out if we use inorganic ligands or inorganic shells, can we make the electronic communication between the nanoparticles better. We are still working on optimizing the synthesis and trying to understand what these surfactants are doing. That is not proving to be as successful as I thought. That's going to be a long project, I think. And we're trying to use a lot of other techniques in collaborations with other people to try to understand the structure. So one of my best friends from my postdoc, Beth Guyton, has joined appointments at the Oak Ridge National Lab in their high resolution.
Once again, Jeff,
So this is the first image she got of our nanoparticles. And what you're looking at are columns of atoms. The larger spheres are the tin sites. The smaller spheres are mixtures of the copper, zinc, and sulfur. And what's important about this is that she's able to take an electron energy loss spectra of a column of atoms and tell us if one of the atoms is not like the others. And from that, we figured out that we have tin atoms where we're not supposed to have them, and that's a trap site. We have copper and zinc pretty randomly oriented. And the other trick is that this electron beam, if you keep it on the particle too long, it evaporates the particle away. And that's another major problem in this field, is how your characterization methods interact with your sample. And it's taken Beth a long time to figure out how to just keep the sample stable and not changing over time. Now, we've also been doing a lot of work with my collaborator Steve Conradson and one of his colleagues, Tom Kaufman, at Los Alamos National Lab. And he does X-ray absorption spectroscopy, which is really useful because it's tunable to the element that you're looking at. Now, what I have not talked at length about is that copper and zinc you can't tell apart by X-ray diffraction because they're right next to each other on the periodic table. But with XFs, you can get a picture of local structure. So it's not long-range structure, but you can see what's bonded to what around the copper atoms. And with neutron diffraction, copper and zinc are very different. So there's a theory paper that said that that cartoon I showed you with the 2 coppers, 2 zincs, and then you flip them, if you could get them ordered, the efficiency would be higher. We are not ordering it. I mean, it's totally random in terms of the copper and the zinc. And more importantly, by XFs now we know that the local bonding is also very variable. So there's extra sulfur around the copper, and there's not around the zinc. And you can actually correlate that to the band gap changes that we see after we heat our samples. So we're finally getting an understanding of, I think, of the bonding in our particles. But what I want to highlight is that these kinds of pictures then are not actually representative of certainly probably most samples in real life, but definitely not the ones made by the reaction methods that Ray and I have talked about. So these are 2 cartoons. This is from another theory paper. This is casterite, CZTSE. You could substitute the sulfur. It's the same structure. And another related structure called stannite. Can anybody see what the difference is? The ordering of the atoms is the only difference. So this is the one I showed you. 2 coppers and 2 zincs. 2 coppers and 2 zincs. This one is all copper, and the zinc goes in the middle. And then the top and the bottom. So the stoichiometry is the same. The oxidation states of everything is the same. The local bonding is the same. And there are many more versions of this. So I guess what I would say is, for solid-state chemists, we're used to looking at a unit cell, and then we just assume that that unit cell propagates in 3 dimensions in space. But if you really stop to think about how likely is it that you're mixing 4 different atoms, at low temperature really fast, there's no reason it should be ordered. And so the question is, really, how does that change the electronic properties? So people have tried to calculate that. These are the band structures calculated for the 2 cartoons I just showed you. And in terms of the band gap, there is almost no difference. Both have this direct band gap. I would say certainly within the sensitivity of how we measure band gaps, those are the same. There are subtle features, though. If you look here, there's a splitting here of these 2 bands, but there is not here. And so I'm leaving this sort of as an open-ended question. I think the idealized picture of these unit cells, and then certainly in nanoparticles at least, is not accurate in real life. But the question is that actually important or not? I mean, people are making really good devices. So maybe in this particular system, it doesn't have to be perfect, and you can still get something that has reasonable electronic properties. So this is, I have no idea how, this may be way too complicated to try to teach undergrads, but it's something that graduate students and I are really struggling with and trying to figure out at what level of detail is it important to understand to at least get to our final goal, and at what level is it just that the tools we have today are so much more sensitive than what we had in the past, that we're seeing subtleties and things that maybe have always existed but people just haven't seen it. So with that, let me highlight kind of the National Renewable Energy Lab. It is the only national lab focused on renewable energy, or solely focused, I should say, on renewable energy. And they have this really cool plot that you can check, which is their accredited efficiencies for different kinds of solar cells. I started by talking about first generation, second generation, third generation. Those are all on here. If you make a good solar cell and you want people to actually believe your efficiency, you have to send it to NREL. They measure the efficiency, and then they put it on their chart. So in this case, the materials that I were talking about, CZTSE, is down here. So 11.1 is the current kind of record holder. You can see that multi-junction cells, really complicated cells, are up at about 44%. So there are the whole range for different materials. And so this is something anybody, you can see, you just Google NREL and photovoltaics, they update things. And, sometimes I use this chart to introduce photovoltaics, at least to again, to show the spread, but also the improvement over time. Okay, so with that, just let me thank my group, but again, highlight Shannon, who's graduated, but she did all the synthesis and characterization work that I showed you today. The research for this was all funded by the Center for Revolutionary Solar Photo Conversion, we call it CRISP. It's just a Colorado collaboratory that links CSU, CU Boulder, Colorado School of Mines, and NREL, and we share resources and equipment and students, and it's now being funded by the Research Corporation for Science and Things. So with that, thank you guys very much, and I'm happy to answer any questions.